Hello everyone, this is Dr. Webb and welcome to this abstract algebra video. So in the last couple of videos we've been talking a lot about isomorphisms. So as you recall, an isomorphism is a map between two groups that is a bijection, and it preserves the group operations between the two groups. So what we mean by that is if you do phi of AB, that's going to be equal to phi of A times phi of B for all A and B in the group G. So in this video, we are specifically going to be looking at what are called automorphisms, and this is an isomorphism from a group to itself. So these are isomorphisms where the domain and the range are both the same group. So let's jump in with an example. So our group here is S3, and we have an automorphism phi, and we know that phi sends the 3-cycle 1, 2, 3 to 1, 3, 2, and it sends the 2-cycle 1, 2 to 2, 3. And so we want to figure out where the other elements of S3 get sent to. And so here we can use the fact that phi needs to preserve the group laws to figure this out. So let's do this bit by bit. So we know that phi of 1, 2, 3 gives us 1, 3, 2. And so if we do phi of 1, 2, 3 applied to itself, phi of 1, 2, 3, phi of 1, 2, 3, this should give us phi of 1, 2, 3 times phi of 1, 2, 3 by the rules of isomorphisms. And 1, 2, 3 applied to itself is going to be 1 goes to 2, 2 goes to 3, 3 goes to 1, 1 goes to 2, and then 2 is going to go back around to 1. And so this is giving us phi of 1, 3, 2. On the other hand, this is going to be 1, 3, 2 applied to itself. And so 1, 3, 2, 1 goes to 3, 3 goes to 2. So 1 goes to 2, 2 goes to 1, and 1 goes to 3. And 3 goes to 2, which goes back to 1. So that closes off the cycle. So for this automorphism, the 3-cycle 1, 3, 2 must be sent to 1, 2, 3. And if you think about it, this makes a lot of sense because 1, 2, 3 and 1, 3, 2, these are the only elements of order 3 in S3. And so if 1, 2, 3 is sent to 1, 3, 2, then it makes sense that 1, 3, 2 is sent back to 1, 2, 3. Because as you recall, for an isomorphism, elements have to be sent to other elements of the same order. So now we have phi of 1, 2 is equal to 2, 3. So what happens if we do phi of 1, 2, 3 applied to 1, 2? And so this would be phi of 1, 2, 3 times phi of 1, 2. And so phi of 1, 2, 3 was 1, 3, 2. Phi of 1, 2, we're saying is 2, 3. Okay, so let's finish figuring this out. So 1 goes to 2 and 2 goes to 3. And then 3 goes back to 1, and so that closes off that cycle. And so really here we're figuring out phi of 1, 3. On the other hand, we have 1 goes to 3, and 2 is going to go, 1 goes to 3. 3 goes to 2, which goes back to 1. So phi preserves 1, 3, 1. The 2-cycle 1, 3 is a fixed point of phi. And then last but not least, if we do this in the other order, 1, 2, and then 1, 2, 3. So this would have to be 2, 3 times 1, 3, 2. And phi of 1, 2 times 1, 2, 3. So 1 goes to 2, 2 goes back to 1, so 1 is fixed. 2 goes to 3 and stops there, and 3 goes to 1, which goes back to 2, and so we are calculating phi of 2, 3, and on the other hand, it's going to equal 1 goes to 3, and 3 goes to 2, so 1 goes to 2, and then 2 goes to 1 and ends there, and 3 ends up going to itself. Okay, so here are the other places that phi sends things. And so you can see this is a bijection. This is 1-to-1 and onto. To figure out these values, we used that phi needs to preserve the group operation. Needs to commute. In this case, it actually is commuting with the group operation because we have the same group and the same operation on both sides. Now we haven't done phi of the identity, but phi of the identity has to be sent back to the identity. That's a property of isomorphisms. Okay, and we could go through and check the rest of these, and it's all going to work out just fine. So here is where phi has to send things. Okay, so for any group G, the set of automorphisms on G is denoted AUT, A-U-T of G, short for automorphisms of G. And it turns out that this set of automorphisms out of G, it is a group itself under the operation functional composition. So the identity of this group is just the map that sends every element to itself. So it's the identity map. And so its name makes sense. We're not going to prove this. This will be a problem coming up ahead. But let's do an example. See this. And so we're going to prove that if n is any integer greater than or equal to 2, then the automorphisms on Z mod NZ is isomorphic to the multiplicative group of Z mod NZ. And so let's see why this is true. So recall that Z mod NZ, so this is a group whose operation is addition, and it is a cyclic group of n elements. And let's recall that Z mod NZ has any integer k, so any k that's between 1 and less than n, that is relatively prime, so the GCD of k and n is equal to 1, is a generator for the group. So the generators of Z mod NZ are all the integers less than n, positive integers less than n that are relatively prime to n. And so what this means is that if phi is inside is one of the automorphisms of Z mod NZ, then if we look at phi of 1, let's say 1 gets sent to k, well, 1 is a generator for this, and by the rules of isomorphisms that we've talked about in previous videos, that means whatever it's sent to has to also be a generator. So it must be a generator. And so then that tells us that k is one of these integers, positive integers, less than n, whose GCD with n is equal to 1. Those are precisely the generators of the group. And so phi must be sent to one of these. And then this means then that for any other b in Z mod NZ, well then phi of b is going to be equal to, well, we can think about B as just being 1 added to itself, B times, and so then this is just going to equal, well, since each of these is equal to K, it's going to be congruent to B times K mod N. And so what this is saying is whatever this automorphism is, since 1 is sent to K, then that means that any other element in the group is going to be sent to whatever B times K is mod N, right? And so we can associate phi to K. So understanding this is now going to allow us to build our isomorphism between the automorphisms of Z mod NZ and Z mod NZ star. And so our isomorphism between it, I'm going to call it capital psi. And it's going to be going from, it's going to be mapping the automorphisms of Z mod NZ. So it's a map of maps that sends maps to elements of the multiplicative group mod Z. Okay, and what this map does is psi sends an automorphism to, I'm going to have it send it to whatever phi of 1 goes to. Okay, and so my claim is that this is going to be both one-to-one and onto and preserve the group operation. And so this is going to be a true isomorphism between these. So first, let's show that this map is onto. Okay, so let's let K be something in the multiplicative group mod K, and I claim that there exists a map phi of K that goes from Z mod NZ to itself, so it's an automorphism. Such that phi K of B is equal to B times K mod N. Okay. And so first let's show that this is onto. So in particular, to show that it's onto, all I need to show is that it will generate all of Z mod NZ, but that's simple enough. And so in particular, phi sub K of 1 is equal to 1 times K, which is equal to K. And so since K is a multiplicative, is relatively prime, so since K into N, their GCD, is equal to 1, then K generates Z mod NZ. And so if it generates Z mod NZ, then it has to be onto. So phi mod K is onto. Phi mod K, it's also going to be one-to-one. It's just because Z mod NZ, because K is relatively prime, it has there is some element mod N such that when you do K times that element, it's going to be equal to 1. This is a fact that we've used before, so this is going to mean that it's also one-to-one. And if you do phi sub K, so remember our group operation here is addition, and so phi of A times B is going to be equal to K times A plus B, which is KA plus KB, which is phi sub K of A plus phi sub k of b. And so it plays around with the group operation as well. So phi sub k is a isomorphism, and phi sub k of 1, as we just saw before, sends it to k. And so I found an automorphism that psi will send to 1. So phi sub k is an automorphism, and psi of phi sub k is equal to phi sub k of 1, which is just k. So that shows that so psi hits everything in the multiplicative group of Z mod NZ. Next, we're going to show that this psi is 1 to 1. So to show that psi is 1 to 1, let's suppose that we have two different maps. Let's call it phi and gamma with psi of phi equal to psi of gamma. Okay, then this means that psi of 1, or that phi of 1 is equal to gamma of 1, and let's say that value is, well, let's use k again. Okay, and so then if we look at phi of b, well, this is going to be b times phi of 1, same as we saw before, because it would be phi of 1 added to itself b times, which would be equal to b times k. And this is the same thing that we get if we do gamma of b. So it would be equal to b times gamma of 1, which is also b times k. And so since this is true for all b in Z mod NZ, so phi and gamma are the same maps, same automorphisms. Now the last thing we need to do is show that psi plays around with the group operations between the two groups. So let's recall that the group operations on the automorphisms is going to be functional composition, where we're going to have multiplication is going to be the group operation on Z mod NZ star. And so let's use phi and gamma be two automorphisms. Okay, and so then if we do psi of phi and gamma composed together, well, this is going to be phi of gamma of 1. And so let's let gamma of 1, be k, and let's let phi of 1 equal L. And so then phi of gamma of 1, so this is going to be phi of gamma of 1 is k. And so since phi of 1 is L, phi of k, well, k is 1 plus itself k times, and so this is going to be k times phi of 1, which is going to be k times L. And since k and L are both relatively prime, then this is relatively prime as well. Mod NZ star. And this is equal to L times K, because the multiplication in Z mod n Z star is commutative, which is equal to phi of 1 times gamma of 1, which is equal to psi of phi times psi of gamma, and we're done. And so we have a one-to-one and onto map from the group of automorphisms to Z mod n Z star, and this map preserves the group operations on both sides, and so we have shown the isomorphism between them. Now, last but not least for this video, there is a special type of automorphism called an inner automorphism. And so what an inner automorphism is, and we'll call this phi sub A. And what phi sub A does is it maps G to A times G times A inverse. And so we can do this for any element of G, and it turns out that this subset of automorphisms is called the inner automorphisms, and it is actually a group. So you should double check that this is actually an automorphism, but we have played around with products like this before. And so if you did phi sub A of G H, this would be equal to A G H A inverse, and then in between G and H we can tuck in A inverse A because they're equal to the identity H A inverse, and so this is equal to phi A of G times phi A of H, and so at least this does preserve the group operation as well. It is not very difficult to prove that this is actually one-to-one and onto. For onto, you just do A inverse, whatever thing you're trying to hit, times A, plug that in, then the A and the A inverses on both sides cancel themselves out, and you have what you want. One-to-one, just doing some cancellation shows that it's one-to-one. So these are actually automorphisms in and of themselves, and then the set of these together actually forms a subgroup of the automorphisms, and so this is called the subgroup of inner automorphisms. That is all for this video, and I will see you again soon.